All right. Ooh. Trying to figure out how I'm going to do this without a stylus. I guess I can just use my finger. We'll try it like that. But I'll tell you what I'll do when I get home. Once I get home, I will rewrite all the notes so you guys can. So it's not going to be very neat, but it will be later today. Okay. Sorry about that, guys. Gosh, there's so many things to bring, Okay, so what we did in chapter 2 is we learned how to estimate values of derivatives, right, by getting closer and closer and doing smaller and smaller intervals, you remember? And we did that using a graph or a table. Now is the fun part, honestly. You guys, this is the derivative formulas, which if you've had calculus before, you probably remember the formulas were easier than everything we just did. So from this point kind of forward, it gets a little more fun. So first we're going to talk about the derivative of a constant function. Let's see. So the constant function, like for example, let's say if f of x is equal to 5. So remember back in algebra, if you have y equals 5, that's a horizontal line, right? And it's a horizontal line right here at 0, 5, right? So if this is the origin right here, then a constant function is a horizontal line going through 5, right? So what is the slope of a horizontal line? Anybody? What's the slope? It's 0, right? So what is a derivative? It's the slope of a function. So the derivative of a constant function will always be 0, okay? So if the function is y equals 5 or f of x equals 5, then the derivative of 5 is going to be equal to 0. And if f of x were 7, then still the derivative is going to be equal to 0 because it's a horizontal line, and horizontal lines always have the derivative of 0. So what does this mean? This means that the derivative of a constant is 0. Okay. All right, now that brings us to the derivative of a linear. So what we're saying here is that if f of x is equal to b plus mx, remember mx plus b, then the derivative is going to be whatever the slope is of the line, which should make sense, but I'll draw you a picture too. So for example, if we have f of x equals negative 3 over 2 x plus 5, then the derivative of that function f of x, or f prime of x, is going to be equal to whatever the slope is in the linear function. And the slope of the linear function is what in this case? So, yeah, so negative 3 over 2, right? And this is specifically because the derivative of a function is its slope, right? So if you think about negative 3/2 x plus 5, it would look something like this, right? Where it's crossing the y-axis at 5, and it has a negative, go down 3 over 2, negative slope, right? So it makes sense that if the derivative is the slope of the function, that the derivative of this linear function has to be equal to the slope, which you know is the m part of the mx plus b, right? So the derivative of a term to the first power is its coefficient. So if you said take the derivative of this whole thing, right? This whole negative 3x, negative 3/2 x plus 5. Well, we know that the constant part, the derivative is 0, right? And according to this rule, that if you have a term where you have an x to the first power, right, a variable to the first power, then the derivative of that term is just going to be the coefficient, which should make sense because the slope is the derivative, right, for a linear function. All right, so here's derivatives of constants times a function. So for example, they're trying to get you guys to see how does multiplying a function, any function, by a number on the outside affect the derivative, okay? And it turns out it does not affect the derivative. And this is what I mean. So let's say that the slope here is m, okay? And notice that it's going up 1 and over 1. So slope is 1. Notice here, and remember, slope is derivative, right? Slope here is going to be 3 times m. And where I'm getting the 3 and the 1 is that going from here to here, you're going up 3 and over 1. So in that case, the slope is 3m. Here, the slope is 1/2 m, because notice you're going up 1/2 and over, sorry, up 1 and over 2. So the slope here is 1/2. Same thing here, we've got slope equal to negative 2m. And I'm getting that from just finding 2 points on the graph. I know I'm going a rise of 2 and a run of 1. Okay, so remember, what we're trying to do here is figure out how does a function being multiplied by a constant number, multiple constant, right, a multiple, affect the derivative. It does not, right? Because if you multiply a function by 3, you get 3 times that function. If you compare it to the derivative, all you're going to do is take the 3 out because it doesn't affect it. So what does that mean? If a function is multiplied by a constant, so is its derivative. For example, if I had 7 times some function, then what you could say is the derivative is equal to 7 times the derivative of the function. So in other words, you can just take that and bring it out of the whole thing. And you'll see when I do some examples in a little bit. What I've done so far on this page is kind of showing you, like, why do these little tricks work that I'm about to show you? Okay, now remember there's this other notation called Leibniz. And that's what this d over dx stuff is. And it's, I'm going to go back and forth between Leibniz and prime and all the other methods that I told you, because so does the test does, the Wiley problems does also. So this is the same thing, saying the derivative of some function, f of x, that is being multiplied by c. So all they're saying here is, for example, if I had the derivative of 4 times some function, then you can say that's the same thing as 4 times the derivative of that function. In other words, multiplying a function by a number does not affect the derivative. You can just move it out. All right, so that's one of the functions, and you'll get real good at using those. It's nice when you see that, because you're like, oh, I can get that out of the way, so I don't have to evaluate it or anything. All right, so there's another rule called the power rule, and it says if you're taking the derivative of something that looks like a power, like that, then all you're doing is you're going to multiply the exponent times the number in front, the coefficient. So you're going to get 8x, and then you got to take 1 away from the 2. So that would be 8x to the first, or just 8x. Now notice this is what the rule says. For example, let's say if over here I have d over dx of x to the 5th power. Then that's going to be equal to 5 times 1. Notice how there's a 1 in front of the x, the coefficient. So it would be 5x, and then we have to take that 5 and subtract 1 from it, make it 5x to the 4th. Those of you that have had calculus before, are you kind of remembering these little formulas? Yeah, okay, good. All right, and now there is the derivative of a sum or difference. All this is saying is if I want you to take the derivative of something that has 2 functions being added together, all they're saying here is that it's the same thing as taking the derivative of the first function and adding it to the derivative of the second function. And here they're giving it to you in the same thing for subtraction, right? So if you take the derivative of something that has sum or difference of 2 different functions, you can do the derivative of the first function and then add or subtract the derivative of the second function. In other words, you can split them up, perfectly legal, okay? So let's see, for example, let's say I had, say I wanted you to take the derivative. Uh-oh. Those are you that are on your computers, can you still see? Okay, I can't see here, but we'll just keep going. All right, so let's say I want you to find the derivative of x to the 6th plus x to the 5th. Well, that's the same thing as the derivative of x to the 6th plus the derivative of x to the 5th. You don't even need to write that step, right? But I'm just kind of trying to illustrate this. So that would just be 6x to the 5th power, right? Because you're going to reduce the power by 1, plus 5x to the 4th power. All right, so let's see if some of you guys can help me with these. We're going to find the derivative of h of x. So we would say the derivative for h prime of x is equal to what? What do you guys think? Yeah, 8x, so we're going to move the 8 up front, x, and we have to take the power and reduce it by 1. How about b? We would be finding p prime of t. Yes, sir. Yes, very good. 7t to the 6. Let's make this kind of legible for you guys. All right, I'm actually getting better at writing up here with my finger. In a pinch, right? Okay. Now, believe it or not, these next 3 examples, we are going to use the power rule because all of these can be written as a power, right? So if you use the rule 1 over a to the x equals a to the negative x, you can rewrite 1 over x cubed as x to the negative 3. So we want to find, we're going to differentiate, that means find the derivative. So d over dx of x to the negative 3 power. Now you can see it is a power, and we can use the power rule. So you have to be careful when you're dealing with negatives, guys. So this is just going to be equal, negative 3 comes up front, x, and then we're going to subtract 1 from negative 3, so that becomes negative 4. How's everybody doing so far? Everybody okay? Yeah. If you have questions, you can stop and ask. Okay? All right. All right. So this next one, if you use the rule that, you can rewrite this with an exponent by saying it's x to the a over b power. So what do you think about the square root of x? Square root of x would be x to the what power? You're very close. What did you say? 1/2, yeah. The reason why it's 1/2 is because the exponent is 1 on the x, right? The index is implied, but it is a 2. So we're going to say x to the 1/2 power. So we're going to move the 1/2 in front, x, and we're going to subtract 1 from 1/2, which would give us a negative 1/2. Now, we don't want negative exponents in the final answer, okay? So we're going to rewrite this using algebra. It's 1 over 2x to the positive 1/2 power, right? And then that can be written as 1 over 2 to the square root of x. Okay, any questions so far? How's the pace? Is it okay? Okay, and then C, we're going to use the constant multiple, right? This is a constant multiple. So what we can do before we even take the derivative is get it out of the way, right? So we can say 2 times the derivative of t to the 4.5 power. And then just take the derivative of the t to the 4.5. So if we took the derivative of that, we're going to take 4.5 and multiply it by what's in front. So we'll get 9t, and then we have to take 4.5 and subtract 1 from that to get 3.5. Everybody okay? Looks like some people are still writing. Let me give you a minute. Okay, so let's practice using some of the different rules we learned together. So the derivative here, what do you think? Volunteer? Just using the power rule, straight up, not a trick question. Cool. All right, how about this one? R prime of P Come on, don't leave it hanging. Come on, guys and girls. This is just power rule and sum and difference rule together, right? Yes. Exactly. 5, thank you. Okay, C is kind of the, some of the same. So we've got F prime of X is equal to 10X minus 21X to the second power. And G prime of X, this one's a little bit trickier, right? We're actually going to use the constant multiple rule here because this is the same thing as 1/4 times t squared plus 3. So if we differentiate t squared, well, we know that 1/4 is just going to come out in the front, right? So 1/2 times 1/4 would be 2/4 t to the first. But when we differentiate a constant, what do we get? Remember, think about a constant. It's a horizontal line. What's the derivative of a horizontal line? 0, right? So when we differentiate a constant 3, it just goes away when you're differentiating. Any questions? Oh, and obviously we should reduce that fraction. And another way you might see that in Wiley is something like t over 2 instead of 1/2 t. Okay. Now here's an example. Remember when I first told you about this course, I told you this is more about the applications because you guys are all business majors. So it's more like understanding what the formulas mean, right? So if I ask you to find an equation for a tangent line at x is equal to 1, I'm asking you for the derivative at 1, right? So if you look at this point right here at 1, let's see. I'm going to just pretend, no, that's 10. So yeah, so 1 would be right here, this point right here, right? 1. So what I'm asking you to find is a tangent line, and that means a line that goes through that exactly 1 time, okay? I'm asking you for that. And now you have tools to find that, okay? So that is a line, right? That's a line, a tangent line. So we're talking y equals mx plus b, it's a line. So if we had the slope and we had one more point, we would have the tangent line, right? So let's do that. First, we're gonna find the slope of the tangent line. Okay, so how do we find the slope? We find the derivative, right? So d over dx of the function x cubed plus 2x squared minus 5x plus 7 is equal to, we're going to use the power rule for x cubed, so it'll be 3x squared And then the power rule again for 2x squared. So that would be 4x to the first power. And then remember, if this is a degree 1 term, then the derivative is just its coefficient. And then the derivative of a constant is what, everybody? 0, right? Remember that horizontal line thing, then you won't try and, a lot of times students will try and differentiate a constant when really we like constants because they just go away, right? Or become 0. Okay, so once we found the derivative, now we're going to plug in 1. Because we're interested in the slope or the derivative at 1, right? So if we plug in 1 to the derivative, we get 3 times 1 squared plus 4 times 1 minus 5, which equals 5. Oh, sorry, 2. Looking at something different. 2. Okay, so 2 is the slope of this line. This is the slope. All right, so we did step 1. We found the slope of the tangent line. All right, step 2 is to find a point on the original function. I'm going to move this down. So here we're going to find a point on the original function. Okay, so what we're going to do is find f of 1, since that's what we're interested in, right? So f of 1, you put 1 everywhere you see x in the original function. So we have 1 cubed plus 2 times 1 squared minus 5 times 1 plus 7. And when you do that, you get 5. So we can say that f of 1 equals 5. All right, so now what we have is we have the slope of that blue line, right? The linear line, and now we have a point. So our third step is to use point slope form to find the tangent line. So point slope form is y minus y1 equals m times x minus x1. And we know one y value is 5, right? Right here, 5 and 1. We know the slope is 2. And we know an x value that we're interested in, that's the 1 value. So if you just solve for y here, you'll get 2x plus 3, which is, if you look back at the original diagram, I'll let you finish writing that. Okay, find and interpret the second derivative. So the first derivative of this is going to just be what? Just using the power rule. 2x. Did you say something else besides that? Oh, okay, 2, yeah, 2 to the x to the first. I see what you're saying, yeah. And then the second derivative means that you're taking the derivative of 2x. What's the derivative of 2x? Remember, any term that has a power of 1, if you're making the derivative of that, it's just equal to what?
2.
Yeah, thank you, 2. All right, so what does that mean? Well, you know from algebra in high school that x squared is just a parabola, right? Now, what we know is since this is, if the second derivative is a positive 2, then what's that saying? That's saying is that the derivative is always positive because it's always a positive 2, right? So because it's always positive, that's why we have a concave up graph. And then here's another, b is x cubed. You guys should be familiar with what that looks like. So let's see, the derivative of that using the power rule would just be 3x squared. And the second derivative is going to just be 6x. Now 6x could be, the result of 6x could be positive or negative, right? Depending on the value of x. So if x were negative, then 6 times x is going to be negative, right? If x were a positive number, like let's say 2, then 6 times 2 is a positive 12. So what you can say about that is, since 6x is positive for x greater than 0, in other words, a positive x value, right? Like positive 1 or 2 or 3, if you multiplied it by 6, you'd get a positive number. And 6x is negative for all x is less than 0. Then if you remember back in algebra 2, the cubic function looks something like that, right? And notice that it is concave down when x is less than 0, right? So let's do a little color coding here. So when x is less than 0, that's this part, and it's concave down. And when x is greater than 0, it's concave up. All right, a couple sections ago we did cost and revenue, right? And that was a fun section. That was chapter 2, the last 2 sections. I always find that so interesting. So this idea of the formulas for derivatives can definitely apply to real life situations like revenue and cost. So it tells you that the revenue from producing a certain amount of units of a product is given by that function R of Q 1000 Q minus 3Q squared. So that's the revenue function itself. And it's quadratic, right? So it's probably going to be, it is going to be a parabola, right? First, they ask you to find R of 125. What does that mean, find R of 125? What do they want you to do with that 125 in R? Substitute, right? We're going to substitute it wherever we say CQ in the original function. So we've got 1000 times 125 minus 3 times 125 squared. Let's see. And if you do that, you will get 78,000 $125. And this, what this means is this the revenue if 125 is sold, 125 units are sold. All right, then it says find the derivative of R at 125. So well, first we have to find, before we can find it at 125, we need to find the derivative. So the derivative of this would just be 1,000, right? Because Q is to the first power. So if you take the derivative of a term to the first power, the derivative ends up being the coefficient of that number minus 6Q. So that's the derivative. Now let's find the derivative and evaluate it when Q is 125. So if you put that in your calculator, you'll get $250. And like we talked about in another section when we were doing profit and cost, it's $250 per unit. And this is if an additional unit is sold. Okay, so let's see how you guys do on taking a look at this graph itself. Let's see if you can answer it. Everybody done with this? Okay. Okay, so the figure shows the graph of a cubic polynomial. You know, that's the kind of shape that they usually make, right? It's cubic. Both graphically and algebraically describe the behavior of the derivative of this cubic. Okay, so suppose we move along the curve from left to right. So this is right, for going left to right. To the left of A, the slope. Now, when we talk about slope, slope is either going to be positive or negative, okay? So what's the slope doing to the left of A? It's definitely positive, right? Because you can see that if we draw instantaneous lines, all of those lines are going to be positive. Good. It starts very positive, meaning steep, right? Starts very positive, like those lines are pretty steep in the beginning, right? But then, let me draw them better so you can see. So here it's really steep, right? But here it's not as steep, right? So the steepness, wait a minute, it starts very positive. And okay, and then it's going to decrease. And I don't mean go down, or I don't mean go negative. I mean the slope is going to decrease from a high number to a lower number, right? High steep, little lower steep, right? 0. Okay, until it reaches point A, where the slope is going to be what? What's the slope right here? 0, yeah. All right, so now let's look at between A and C, the slope. It's going to be positive or negative here? Negative, yeah, good. Okay, and between A and B, the slope is doing what? I'm not meaning positive or negative, but is the slope decreasing or is it increasing? So notice here between A and B, oops, let me get a different color here. Between A and B, the slope is decreasing, right? That's just between A and B. Let me draw those lines a little better. So here's the slope, right? Well, that's not very good. Yeah. Okay, and what it's doing is it's getting more negative, right? That's why it's decreasing. It's getting more and more negative. And it is most negative at point what? Right through here, right? It's hard to draw these lines. There. No, that's still not. It's hard to do it with my finger. Sorry, guys. Ah, I can't get close enough. I'll do it there. Okay, so it doesn't mean that it's if it gets more negative, that means it's decreasing. If it gets less negative, that means it's increasing. Okay, so it's most negative at point B. And then now let's talk about between B and C. Okay, between B and C, the slope is negative, right? Because it's going down. But it's most negative here, but then it gets, oh, see, it's hard to do this. And I'm just looking at instantaneous points. So let's say this point right there is a little less negative, right? So it's increasing. And what happens at C? What's the slope? What'd you say? Yeah, 0. And then from C to the right, the slope is positive or negative? Yeah, positive, right? Because it's going up. Positive. And is it increasing or decreasing, do you think? Because those two lines I just drew are pretty good. Increasing, right? Because it gets more steep. All right, good. This example will be good for Wiley problems, okay? And of course, it'll be done neater for you later. Okay, and then let me show you algebraically. Not that we do too much of this in this class, but since that question was asked, algebraically. Did I say this? This is graphically. Okay, so a couple of things we know, and they told us that f is cubic. So we can say that the standard form of a cubic would be some coefficient a x cubed plus another coefficient b x squared plus c times x plus d. So algebraically, what we could do is take a look at the derivative of it. So you would have 3ax squared, right, using the power rule. We're just taking 3, multiplying it by the coefficient, and reducing the power by 1. And then to differentiate bx squared, it would just be 2b x. And then since the x has a positive 1 power, we know that the derivative of that term is going to be just the coefficient c, and d is meant to be a constant, and we know that the derivative of a constant is 0. Okay, so based on this, first of all, we know that this is quadratic, right? So it's going to be a parabola. And does the parabola, is it going to open up or is it going to open down? Based on that 3 coefficient. Yeah, definitely up, right? I'm trying to remind you guys of the algebra stuff that you kind of need to know for this class. But yeah, if that was a -3, then it would be concave down, right? It would open down. But algebraically speaking, we know a little something about this graph just by kind of looking at it algebraically. We know a lot more about it here, right? Looking at it graphically. Okay, so far we know the derivative of a constant number, the derivative of a term that has 1 as a exponent, and we know the power rule, and we know the sum and difference rule, and we know the constant multiple rule, right? Like a constant multiple of a function does not affect the derivative. You just get to move it out, which we like. All right, so here's some more rules for when you take derivatives of exponential and logarithmic functions. And it's just, if you've never seen these formulas, they're not difficult by any means. You just have to know when to spot, oh, that's a log function or that's an exponential function. That's all. But the formula is kind of like the power function, right? It's not that hard of a formula once you do it a couple of times. Okay. Okay, so let's do for example here. If I wanted to take the derivative of something like, let's say, 2 to the x power. Well, using the formula, I'm going to do the natural log of my a value. My a value in this example is 2, so you can take the natural log of 2 and then multiply it by the a value again, 2 to the x power. Here we have the derivative of e to the x. We like this because the derivative is the same thing as itself, right? So e to if the original function is e to the x, then so is the derivative. We like that. That's an easy thing. That's kind of like the constant rule, right? That's going away. So e to the x are easy problems. So let's say I had something like the derivative of 2e to the x. Well, we know that constant multiple 2 does not affect the derivative, right? So this is the same thing as saying 2 times the derivative of e to the x, which would just equal 2 times e to the x. Two is still there because of the constant multiple rule. E to the x is still there because it is its own derivative. All right, and here's e to the kt. So for example, if I had something like d over dx Wait, that looks like some foreign equals, let's see. e to the 4t. No, I don't want that, sorry. I don't want equals. I want here. Okay, so if I want to take the derivative of e to the 4t, then what I have to do according to this formula is move the 4 to the front and just write e to the 4t. Okay, so let's take a couple of these rules and put them together. So if we differentiate 2 times something, then that's the same thing as 2 times the derivative of 3 to the x power. And then using sum and difference, and then now multiple again, 5 comes out, d over dx of e to the x. And now we'll just do 2, and 3 to the x is just natural log of 3 times 3 to the x. This is plus 5, and the derivative of e to the x is just e to the x. How are we doing so far? Everybody okay? All right. Okay, so oh, and let's start using this other Leibniz. dp over dt, that means the same thing as p prime, okay, is going to equal the derivative of a constant is 0. Using the power rule, this would be 6x minus 7 can come out, right? And then we have to use the rule for the e to the kt power. So we're going to do the k, which would be negative 0.2. And then we'll just do e to the negative 0.2 x. Now, we can simplify this, right, by getting rid of the 0 and multiplying this out. Point 2x. Now, sometimes if they're just asking you for a formula and they're not asking you to use the formula for anything, you could just leave it like that. But they're not going to mark you wrong if you simplify something, okay? Most of the time you'll simplify it if they're asking you to use the formula for something. Like if they wanted to know the derivative at a specific number, right? Then you don't have to simplify it, because if you put the number in there, you know, you're still going to get the same answer in the end. Okay, so here, let's see, and remember, they're asking for the derivative, so, and I'm using this other notation. So the derivative of p at t is equal to, we're going to use the power rule first, right? So we get 9t squared plus, remember, e to the x is the derivative of e to x is just e to the x, and constant multiple, we're just going to have 2e to the x, or in this case, t. So whenever you have like 5e to the x power, 6e to the x power, it's just going to be the same thing that you started with, because of the constant multiple rule and the e to the x rule. okay, f prime of x here. So what's the derivative of 2e to the x? See who was listening to me just now. What's the derivative of that first term, 2e to the x? Yeah, thank you. 2e to the x. 2 because the constant multiple, e to the x because the derivative of e to the x is e to the x. And then x squared, of course, we're just going to use the power rule, and that would be just 2x to the first power, or better, 2x. All right, let's say I'm trying to use all kinds of different notation for derivatives. So if I have y, then I can say y prime, that's another shortcut way of saying the derivative of that function y, is equal to, well, we're going to take the 5 out because it's a constant multiple, right? But then we're going to take the rule for exponentials, and we're going to say, we're going to use the natural log of the base 5, and then throw in 5 to the t power. That's just using the formula straight up. Plus 6 is a multiple, constant multiple, and we're going to use the exponential rule. So we're going to take the natural log of the base 6 and multiply it by 6 to the t power. Now, I was talking before about formulas, and sometimes if they ask you for a formula, this is perfectly acceptable. Now, you could simplify some of this, right? Because the natural log of 5 is just a number. But if they're asking you for a formula, this is acceptable, okay? Sometimes it's if you're going to find a value of that derivative, you know, like y prime of 3, for example, you might want to shorten that up a little bit before you plug in your value, you know, like find out what is 5 times the natural log of 5. But you don't have to, right? Because if you plug in, if you simplify that and then you plug in something for t, you're going to get the same thing. Does that make sense? I'm trying to save you a little bit of time. Okay. All right, let's see. E, let's say, okay, so y prime, again, is going to be the constant multiple, 5 comes out. Then we're going to use the exponential rule. So we're going to do natural log of the base 2, and then just throw in there 2 to the x power, minus the derivative of 5x is what? Remember, 5x is to the first power. It's just 5, right? It's just 5. And then what's the derivative of a constant? 0. Remember, constant is a horizontal line, and the slope of a horizontal line is 0. Good. Okay, where was I? Yeah, so that's your final answer. Okay, and F, one more before we learn a little something new. Okay, so we know that 12.41, because it's a constant multiple, right? It's being multiplied, comes out. We don't have to worry about finding the derivative of that. But we've got the base in this case is 0.94. And then we'll just throw in 0.94 to the t power. And you're done. All right. We'll just do, I think we're going to just do the rest of these formulas, and then we'll leave example 4 and 5 and 6 and the rest of it for next class. Okay, so derivative of the natural log. It has its rule, right? This is the new rule. These we did on the last page. So all of these are not new. Okay, so if we're trying to differentiate this, so let me just do a quick example. D over dx. Let's say I want to do d over dx of ln of 5. Then that's just going to be 1/5. So if we differentiate this one, we get 5 comes out, right? Because it's a constant multiple. And the derivative of the ln of something is just 1 over that something. So this is just 1 over t. And then we've got 7 constant multiple. E to the x is just e to the x. Power rule here would be 8t. And the derivative of any constant, remember constant is a horizontal line, so it's 0, right? You're done there. And last part here, derivative here, r prime of q is going to be, we're going to use power rule for q squared, right? So that would end up being 2q to the first power minus 2 is constant multiple, so it's going to come out, right? And the formula for finding the derivative of the ln of something is just 1 over that something. So we've got 2 times 1 over q. And then we can simplify that a little more. Yeah, and I think that the rest of the examples, 4 through 8, kind of, I can chunk them together better in the next class. I don't want to do just a couple because then you won't maybe understand it as well. Thank you for putting up with me forgetting my stylus.
Thank you.
Thank you.
Is that you, Sean?
Thank you.
Dylan, Caroline, Daphne, Grady, Grady, Giovanni, Thomas Mills, Thomas Boyd, Richard Cloud, Zach, Emily. Okay, I'm pregnant. Will Lyons, Will Hannah, Drew Fitzpatrick, Ian Oliver, Jesus, Matt Leonard, Ainsley Duncan, Sophia. Thanks, guys. Enjoy this beautiful weather.
Yeah, like I texted you like about my hand. Turns out I'm gonna need surgery.
No.
Yeah, and like in like a cast for a little bit. So I just wanted to let you know, like,
What's your plan? What's your plan? I mean, I'm sure you thought about like, okay, so what am I gonna do?
yeah, like I'm hoping to do everything I
I guess
can.
you're gonna have to type with your left hand.
I
You
have
have
voice
to print out the note.
Yeah, but like I'm just like a little worried about this class.
Yeah.
Cause like I'm doing pretty well, and I don't want to like fall behind.
I know you are doing really well. Well, this is what I would suggest. I think, pay attention to my Spanish class, and don't worry about writing. And print the notes out later.
That's what I was planning on doing.
Yeah. And just going over it, and if you're like, oh, I don't know what you mean here,
Okay.
then that's when you just text me and say, hey, can we
Okay.
work online?
And then I'm not too sure how I'm gonna do this.
Or you're just gonna type with your left hand.
Okay.
Yeah.
I mean, okay. Alright. I need like a time.
I hope you know that I'm pretty weak.
I know.